So welcome to this next class. What are we going to do now? Well, right now last class we came up with some semblance of a procedure that we have been implicitly applying to synthesize our control structures. Yeah, we want to refine it further, and before refining it further I'd like to draw your attention to some aspects. What is the control system doing? Okay, if you think about it, there's essentially two tasks. Number one is stabilization. What do we mean by stabilization? What do we mean by stabilization? Something that's unstable needs to be stabilized. Yeah, a missile is unstable. You have to have a control system so that an aeroplane is fundamentally unstable. Unless you have appropriate control systems, only then will it fly in a stable way, right? Exothermic reactors can be unstable, their temperature can run away. Well, you have to have a temperature controller. Levels are not unstable, but they are on the border of stability and instability. What is instability? If you look at instability, an unstable response, output versus time, unstable response would blow up, something like this. Level or inventories in general behave something like, where y is a level, if there is a mismatch, it either continues to build up or continues to deplete. Yeah, so they are on the border of stability and instability. Okay, so anything and everything that shows this behavior, which behaves like an integrator or is inherently unstable, you have to install a controller or a control system to stabilize whatever is unstable in your process, right? So there is this stabilization function. Okay, what's the next function?
Maintain fixed output or whatever kind of profile you
Well, I was thinking of more. Stabilization is a very general thing. Okay, so something which is more general is what I am looking for. First you stabilize your process, then you run it in a way so that it is what? It is as economical as can be. First function is stabilization, next function is what? Economics. Economic operation. Okay, an economic operation could be in terms of what? What is the throughput that you want? Product quality that is desired. What else? Active constraints. You could also have things that are unconstrained. Okay, what do I mean by unconstrained? I think I need to qualify that a little more, explain that a little more. But the basic point is your control system must be designed to first stabilize the process and then ensure that whatever set points you are feeding, it is ensuring in some sense economic operation. What do you mean by economic operation? A, you are producing as much as is desired. B, you are producing only as pure a product as is desired, not over purifying and not under purifying, because under purified product won't sell. Over purified will typically mean that you are selling something precious and not charging for it. Yeah, okay. And of course, we saw last time, this column should be on flooding, the other column should also be at flooding, level should be max, temperature should be max, etc., etc. So there are these active constraints. You must design your control system so that you can operate your process as close as possible, and where possible at the constraint limit. Okay, we saw this last time, I hope you remember. But the general philosophical point is the control system is doing these two tasks: stabilization / regulation, let's call it. And when we say regulation, that means inventories need to be regulated. Every inventory, whether it is gas or liquid, needs to be regulated. Okay, so process stabilization and regulation, and then the next level is economic operation. Okay, now what do I want to say next is, now let's look at degrees of freedom. Every process has got, we discussed this, more number of valves than steady state degrees of freedom. For example, a distillation column excluding the feed has got 5 valves. 3 of those valves are used for pressure and 2 level and controlling, for pressure control and controlling 2 levels. That leaves you 2 valves, which are your steady state degrees of freedom, right? So now when you are trying to optimize process operation, what you do is you have some objective function j, okay, and let us say you are trying to maximize your objective function j, and j could be, for example, revenue earned by sale of product minus cost of raw materials minus cost of energy. Okay, so that's your hourly operating profit, right? It could be dollars or steam consumption per kg product produced. It could be simply production rate of the value added product, okay, of your main product, etc., etc. Okay, so you want to maximize over your steady state degrees of freedom. You are your steady state degrees of freedom, okay, and when you optimize, you find, let us say there are n decision variables. Of these n, at the optimum there are m less than n constraints that are active, okay, less than or equal to, actually m could be equal to n, and then there are n minus m unconstrained degrees of freedom that are left. What I mean to say is, if there are so many degrees of freedom, you want to drive product column to flooding, you want to drive recycle column to flooding, you want to drive reactor temperature to maximum, you want to drive the reactor level to maximum. What that means is 4 degrees of freedom are getting exhausted in order to make these constraints active. I am just taking from the example that we did last time. 4 degrees of freedom get exhausted this way. Yeah, whatever is left, they are unconstrained degrees of freedom. Does that make sense or no? Okay, and there you need to think that, well, for example, composition, let's see, for example, I can't think of something for that other process. Okay, for example, let us say the reactor temperature cannot be kept at maximum, because if you take the reactor temperature too high, because the activation of energy of the side reaction is much more than the main reaction, your selectivity goes down tremendously. So even though you would like to maximize the temperature for greater conversion, it turns out that you start producing so much junk at the maximum allowable reactor operating temperature that you are better off holding the reactor at some lower temperature. If you reduce the temperature too much, what happens? Conversion goes down. Conversion goes down, then your recycle cost goes up. Okay, so now this is an unconstrained degree of freedom. There is the low temperature limit and there is the high temperature limit. Just by arguing about it, it is clear to me that I should not operate at the low temperature limit because my recycle cost blows up. I should not operate at the high temperature limit because I am producing too much side product, my selectivity goes for a toss. A good value of the temperature is somewhere in between this high and low limit. These are unconstrained degrees of freedom, where the exact best value needs to be figured out, either by a model, by an optimizer, or some good engineering sense. Okay, so there are constraints that must be active. Whatever is left is what? Those are your unconstrained degrees of freedom. And now the question is, what are those set points that I need to choose? Okay, I would like to bring your attention to something like this. See, for example, let us say there is a 100-meter race. Okay, this is borrowed from Sigurd Skogstad. Okay, if there is a 100-meter race, what is your optimal running policy? Just gas up, just press the pedal as hard as you can at its limit, run as fast as you can. That's your optimal operating policy for what? A 100-meter race. Let's say it's a 40-kilometer marathon. Now what is your optimal policy?
While maintaining the position.
Exactly. So now it's not so clear. And the the route that you're supposed to take is not as flat. Sometimes there is downslope, sometimes there is upslope, sometimes you have to climb a hill, sometimes you have to go downhill. So now your optimal policy is not so clear. But then you start thinking about it. What should I do? If I have to run a marathon race and I have to do it to minimize my race completion time so that I may win, what should I do? Everybody agrees running the fastest is not a good idea because I'll simply drop dead.
Speed will be maintained anyhow.
Okay, but then there is uphill and then there is downhill. If you try to maintain the same speed uphill,
Yes.
probably your heart will collapse. And when you are going downhill, if you are braking, then again that's not optimal, right? You are unnecessarily slowing yourself down. Yes or no? Okay. So maybe what I should be doing is, these days you get those pulse meters or heartbeat meters,
Yes.
right? Or maybe those calorie meters. So maybe you need to adjust your running speed so that your heartbeat remains constant. How's that? That sounds more reasonable, right? Now the only thing that the operator has to specify or the marathon runner has to figure out for himself is what is my optimal level of my heartbeat, right? If I maintain that for mild ups and downs, turns and twists, my running policy, my operating policy is, if not optimal, at least near optimal. Does that make sense or no? So what have I done? I just gave you an example. What have I done?
You've chosen a set point where it can be set to maximum.
Yeah, so I am trying to choose a controlled variable. I am trying to choose a CV. So there is an unconstrained degree of freedom. That means I can control one thing in my process. I want to figure out what is that one thing that I need to control so that my operation is optimal. Does this make sense or no? What is that one thing? See, if it is an active constraint, then it's very clear. Press the gas, full pedal. If the column has to be operated at flooding limit, very simple, operate it at flooding limit. Right? If the reactor has to be operated at maximum level, very simple, operate it at maximum level. Right? It is in the case where you really don't know, there is one trade-off here or at this end and there is another trade-off at that end. Low temperature, conversion goes down dramatically. High temperature, selectivity goes for a toss. Somewhere in the middle is my optimal operating temperature, right? And this, the value of this optimal operating temperature should not change by much if I am changing my throughput. Then it is a good CV, because regardless of my throughput, regardless of disturbances, the optimal value of that set point remains close to whatever I am inputting. Does that make sense or no? Alright. So, you see, I have a, let me explain it a little more. I think this requires some elaboration. Let us say there is one unconstrained, one degree of freedom that I need to choose. In this marathon runner example, I had so many options. I could have controlled speed, okay, I could have controlled, I don't know, level of lactic acid in my muscles, heartbeat, okay. Simplest thing to do is speed, okay, or speed or what, effort, okay. Effort is like the valve, how much effort you are putting in. The more effort you put in, the more speed you have, okay. So one fellow says, okay, maximize your effort. For a marathon, that's not a good policy, because you don't have so much gas in you, okay. Next fellow says, now adjust your effort so that your speed remains constant, okay. Next fellow says, no, you know, there are ups and downs, certainly holding constant speed is not a good idea when you are going uphill, and holding the speed at the same value when you are going downhill is definitely not a good idea. This is just common sense, right? So next fellow says, no, you know, maybe what you need to do is heartbeat, okay. So you adjust your effort to maintain the heartbeat constant. Then another fellow comes in and says, well, you know, when you're fresh, your muscles are fresh, but as you run, your muscles tire, okay, and that degree of tiredness is indicated by the amount of, I don't know, some chemical that accumulates in your muscles, which is measurable. Let's say, I'm saying lactic acid, it may be something else, I don't know, okay, and I have a, how much lactic acid is there in my muscles, I know that. So then what I need to do is, I need to reduce my heartbeat in order to maintain what?
Same concentration of that chemical.
Lactic acid, right? Slowly but surely I am maintaining something constant, but what is that something? That is not very obvious. It could be dumb, it could be a dumb choice. Dumb choice is maximize effort, daudo or mar jao. That's as good as saying that, run and bloody collapse, right? Other is, okay, constant speed, that's also a dumb choice. Heartbeat reasonable, but it doesn't account for, you know, over 40 kilometers you are going to tire. You know, you can have a high heartbeat in the beginning because you are fresh, that same heartbeat being maintained towards the 35th kilometer is probably tiring you much more, right? So the moment you start thinking of this, so what is a sound controlled variable? And when I say sound, I mean economically sound. Now this is a question, the better your answer, able to answer it, the better your operation, okay. I cannot claim, nobody can, not me, nobody can claim that this is the best, okay. You can always figure out CVs that are better. The whole idea is, for unconstrained degrees of freedom, what should I specify, so that once I have specified it, my operation is optimal here. Not only here, even if my throughput has changed by 20%, it is still optimal, or at least near optimal. Even if my throughput has decreased by 20%, it is still optimal. What is that variable? Okay, do you see what I am saying? So the whole idea is, well, you can draw it in a figure. Let's say this is J, this is a disturbance. My disturbance could be a change in the throughput, my disturbance could be change in the impurities in the raw material, whatever. Okay, I want to choose a CV you see, you can choose any CV you want and you can optimize and figure out, well, for the given value of the disturbance, this is my if I am controlling CV1, this is how J varies. Okay, well, let us see, this is not D, this is CV. Okay, so the optimal value of my CV is this for some value of the disturbance. Okay, if you plot it against the disturbance, what you really want is that no matter what the disturbance, the CV that I have chosen, its optimal value should be flat. That means if my disturbance is this, as long as I have chosen the right set point for that CV, even if my disturbance changes in this band, my J is not getting affected by much. Okay, such a choice of a CV is a good choice for optimal operation, for economically sound operation. Such controlled variables would be referred to as economically sound controlled variables. Okay, and the whole idea is how to figure out these economically sound CVs, and there is no, what should I say, the better the engineer, the better his understanding of the process. Just like I walked you through that marathon runner example, the more you try to understand the process of running a marathon race, you will figure out that there is some policy that holding which constant is near optimal, if not optimal, near optimal. If you talk to racers, they will tell you run like this, conserve energy for the last burst, okay, and then the final thing is when should I take that burst. You see, runners, if you talk to runners, they will probably talk like this, when do I take that last burst, and their whole mind is processing this, what should be my speed right now, others are overtaking me, should I increase my speed, should I decrease my speed, etc., etc., etc. Okay, the point is, we would like our control system to be simple. What do you mean by simple? Just a second. So suppose I had this situation, I was controlling a CV with respect to which my objective function shows a very sharp dip. If my objective function is showing a very sharp dip, that means if my disturbance changes by a small amount, I am taking a big penalty. This penalty is an economic penalty. Yeah, here I am trying to minimize J, I am not maximizing J but minimizing J. I want to operate at, for example, minimum energy cost, okay, negative of profit, negative of revenue, something like that. Okay, so this is an economic loss. On the other hand, if I am controlling something with respect to which the optimum surface is very flat, okay, then what that means is if I deviate far away from here or far away from, if my disturbance moves this way or that way, I am still, if not exactly optimal, near optimal, right, and then my headache is over. Why is my headache over? I just put in a control loop that tries to control that economically sound controlled variable by adjusting the valve that is unconstrained. Does that make sense or no? Okay, so I just put that loop, I input a set point, and this set point need not be worried about, regardless of what my throughput is, what my feed composition is, regardless of the disturbances. The operating policy becomes very simple. It is simple to implement. Do you see what I am saying? Yes or no? You see, when you know that this column has to be operated at flooding limit, or heater duty should be maximum, it's very simple to do that. Just fire the heater, just turn the gas full, right? Heater is running at max capacity. Small 100-meter race, well, just put in as much effort as you are capable of, right? So dealing with active constraints is actually straightforward. Yeah, it is this unconstrained degree of freedom. Dealing with that is, it can be made progressively better by understanding more and more about the process. The simple example that I gave you should convince you of that. Just as objective is minimize race time, marathon, what is the optimal policy? How should I vary my effort so that my clock time is minimized, right? All right. So what are we talking about? We are talking about there are degrees of freedom. Of these, at the optimum, some will be active, okay, the rest would be unconstrained. When you are designing a control system, what do you need to do about active constraints? You need to make sure that those constraint variables, well, okay, we will talk about this a little more. Active constraint means, okay, so if my gas pedal has to be maxed out, you have to max it out. Okay. So unconstrained degrees of DOFs. What do you need to do about unconstrained degrees of freedom? You need to figure out sound CVs, economically sound CVs. Which are they? That's a question. That question remains. Okay, that question must be addressed by thinking about the process. Okay, for active constraints, there are some rules of thumb. You want that your column should be as close as possible to flooding. Okay, or let us say you want boil up to be maximum. Okay, now let us say this is your column. I am just giving you an example to make a point. Okay, let us say what you have in place is a control system that does this, conventional, simple minded, adjusts the steam to maintain a tray temperature so that light stuff doesn't, that is what you would do if you do not think about constraints. Okay, and let us say level control is, I do not know, maybe this way. Now your analysis tells you that this column must be run at maximum boil up. Okay, if this column is to be run at maximum boil up, then what would you do? So there is this feed, that is the throughput manipulator. Now since your steam is already under temperature control, what you will do is you will measure the boil up. If it is approaching maximum, then what will you do? You will adjust what you are putting in, you will reduce what you are putting in, right. So this I will call an active constraint controller. Okay. To maintain the boil up at maximum, what I am doing is I am adjusting the feed to the column. Okay. I give you an alternative, and it will be obvious that the difference between these two alternatives would become obvious. So there is the feed to the column. What I do then is I maintain the boil up by adjusting the steam. Okay, I do not use steam for temperature control. What I do is I do temperature control this way, and of course level control is as before. Compare these two alternatives. Where do you think you will get tighter boil up control, and why? These are two alternatives doing the same thing. My analysis tells me I want boil up to be near max. Okay, if I want the boil up to be near max, then what? Will scheme 1, let's call this scheme 1, let's call this scheme 2. Which one do you think would be a better scheme, 1 or 2? Just think the lag. If I make a change in the feed flow, okay, what will happen to the boil up? You think it will respond immediately? Versus if I make a change in the steam, response of boil up will be faster to which one? In the second case. So I change the steam, boil up responds immediately. I change the feed, what happens is temperature cools down or increases. In response to that, the temperature controller adjusts the steam. In response to that, the boil up changes. You see, there is this additional lag associated with the temperature having to respond to a change in the feed before the boil up changed. Yes or no? Yeah. That being the case, I can look at this scheme and say that with reasonable certainty that, look, if you want tight boil up control, then this is the better option. Option 2 is the better one, because you are directly controlling the constraint variable with a handle which is close by, with a manipulation handle, with a valve that is close by. What are you doing here? Your manipulation handle is further away, if not far away, it is further away than, right, and therefore your control, your dynamics are slower. If your dynamics are slower, your control cannot be as tight. If your control cannot be as tight, what you will find is that the boil up is actually varying like this, and therefore you cannot, you see, if this is my 100% limit, you will have to operate like this. In this case, because the steam is right there, there will be some variability in the steam, but it will be very small. Flow control will be very tight, right? If the flow control is going to be tight, well, you are almost at 100% level. Yes or no? Does that make sense or no? So this scheme will allow me to operate closer to the max boil up limit, which comes from the flooding limit, compared to scheme 1. Yes or no? Yeah. So what am I trying to say? You active constraints need to be controlled as tight as possible. Yeah. You want to minimize the back off. For tight control, what do you need? You need a manipulation handle that is as close as possible. Yes or no? Okay. So for tight active constraint, the rule of thumb is choose manipulated variables for active constraint control that are as close as possible to the, not the CV, constraint, to the constraint. Does this make sense or no? These are just simple minded things. I have taken a long time to explain this, but when we start looking at processes, you know, what should I do? Where should my throughput manipulator be? Okay, should I control the column temperature using the steam, or should I control it using the feed, or maybe should I control it using the reflux, or should I not even control it? Yeah, these things need to be kept in mind when you are designing a control system for a complex process, with prior knowledge of what are the constraints that are active. Then, you know, that process may not be feasible economically to begin with. Second thing you need is, whatever you are selling must command a premium. For example, if the government brings in a regulation that says this additive cannot be added to petrol, you have a plant that is running to making that additive, Government has banned it. That's it. That process is dead. You see what I am saying? So, some basic things need to be satisfied. Energy is much cheaper than petrol or benzene or acetic acid or whatever, okay, per kg cost. Whatever you are producing should be much more, not if not much more, at least 20%, 30% more price per kg than what you are putting in the raw materials. Unless these things are met, it doesn't make sense to have that process, right?
But my question
What is your
basically
question?
was, in the first scheme, last class, when we did this, we wanted to go for first scheme because throughput was the main thing we needed to control.
Yeah, so
But
through
this
no,
time we
just
want-
a second. So throughput, maximizing throughput makes sense when economically, when there is sufficient demand, but not too much supply. For example, there is a new market that's opening up. You found a technology, nobody else can make that. You have a patent for it. There is sufficient demand in the market. For example, PET. You know these Coca-Cola bottles.
Yes.
Eastman
Right.
Chemical makes it. Okay. When they came in, they were the only manufacturers. So their whole idea was make as much as you want because there are n number of guys who will take it at whatever price we want. So if I want to make money, that's the way to make money. Just maximize your production. Okay. Competitors caught up 2 years, 3 years down the line, but for those 2-3 years, your policy was jack it up. The moment a competitor came in, well, your price went down immediately. Same thing happens in shops. There is one guy in shopping center, he says, you want to take it, otherwise buzz off. Today we have Mahir and Supers, and now both behave very well. I'll give you 5 rupees off this juice packet, that fellow gives 7 rupees off this juice packet. You see how fragile economics is. Yes or no? Okay, so when we are saying maximize production, I guarantee you it will never be true that for this process maximizing production is always optimal through the whole life of that plant. No, maybe for a year when competitors are trying to catch up. The moment competition comes in, then you have to move like a cartel. Boss, don't glut the market, you are also going to get screwed, I am also going to get screwed. Don't produce too much tomatoes. We have to make sure that the prices remain such that, do you see what I am saying?
Yes.
We don't kill each other. Then it becomes a cartel. Okay, if you are first in the market, maximizing production makes sense. The moment competition comes in, then you need to have some sort of understanding at some level that look, we should not kill each other by glutting the market. Yes or no? So that is why even though I said J is, for example, raw material price minus this, I am not very comfortable with that. Why am I not very comfortable with that? Because prices are very fragile. One war in Libya and then that's it. One government regulation, then that's it. One Standard and Poor rating goes this way, that's it. These things are too fragile. Yes or no? So, but the point is you need to still think it out. If my product is commanding a premium compared to my raw material, and if there is sufficient demand, even though there is competition, it will definitely pay you to think what is the best way of running my process. Okay, regardless of the economic scenario. Economic scenario can change such that raw material is more expensive than the product. Well, then that plant has to be shut down. As simple as that. Or maybe a catalyst got invented, or maybe there is a market that came up which was commanding so much more premium for the product that they are cumene. Earlier it used to go to nylon. Now most of it goes to phenol resins. You know, those gums and adhesives and okay. So production capacity is what it is. The downstream product mix has changed. You see what I am saying? So the point is J is equal to product minus raw material minus energy. That's very fine. But how the hell do you predict? How the hell do you guarantee stability of those product prices and raw material prices, etc., etc., etc.? Nobody can. Okay, so therefore economies rise and fall, and that uncertainty, I don't think you can do anything about it. It's fine and dandy to talk about it. Look, this was my objective function, this is the price I assumed, I put it into an optimizer, this is the result that it gave, these are the active constraints, these are unconstrained degrees of freedom. As a systematic way of understanding the process, that's fine, but I still don't think, I'm still not convinced that that's the best way of running the process. How much to produce, what quality to produce, that is best left to market analysts who will say, look, who will do their understanding with their cartel players, etc., and say, look, your plant for the next 2 months production objective is so much of product, this quality, this product mix. Winter season is coming, heating oil demand is going to go up, gasoline demand, therefore jack down the gasoline that you are producing, jack up the heating oil, because winter season is coming, right?
Basically, objective function is fragile, so we have to.
Yeah, so my concern with this approach is the objective function itself is quite fragile if it is based purely on prices. Okay, so what I prefer in my thinking is, some economist should tell me what to produce, how much to produce. Then I can do it in a way that economist can also tell me produce as much as you can, because we are the only we have a monopoly over the market for the next 2 years, because this is our patent for the next 5 years. Even to copy it will take 2 years, right? Fair enough, but then I am told maximize production. If an idiot like me comes, this is the price, this is this, what is the best thing, always the answer will be maximize production. And if idiots like me are there in every company, they'll all maximize production, nobody will buy it, our warehouses will get filled up with the product, we will not be able to sell it, we will be paying guys, and everybody will kill each other. Do you see what I am saying? So don't swear by economics, I don't swear by economics, but certainly what is the most efficient way, how should I run this process, so that for this production rate or for this throughput my energy consumption is minimized. Certainly as an engineer I can figure out, yeah, reactor level should be highest because the conversion is maximum, therefore amount to be recycled is minimum, therefore the amount of steam required to recycle the unreacted reactant is minimum. This will be true whether I am operating at 100 kilomoles per hour production rate or 150 kilomoles per hour production rate. Yes or no? So it's an active constraint. Comes out purely by engineering common sense. Well, I need to run my reactor at maximum A composition, because if the A composition is high, B composition is less, side reaction is therefore less, because the reaction chemistry dictates that the reactor should be operated with B limiting, because if B becomes too much side product gets formed. How do I maximize A recycle? By maximizing my boil up, because whatever I am boiling up minus the reflux is what is getting recycled, right? Now whether my production rate is 100, 120, 150, this thing is going to be true regardless of the economic situation. As long as my product is desirable, this is what I should be doing. So reactor level should be max, recycle column should be operated at max boil up or flooding limit. Depending on the kinetics, I may also say that the reactor should be operated at maximum temperature, because the kinetics are such that jacking up the temperature has only a very marginal effect on selectivity, right, which I am able to overcome by ensuring maximum excess ratio, right. So then I have got 3 constraints: active, maximum level, maximum temperature, flooding limit on the recycle column. This has come purely by what? Applying engineering common sense. Okay, I repeat this again. It's very easy today to formulate a problem, some objective function, a set of constraints, shove it into an optimizer, it will spit out some results. This and this is active. Okay, the whole thing is meaningless unless you try and interpret why the hell is this active, why the hell is my optimizer saying maximum level, why the hell is my optimizer saying maximum boil up, why the hell is my optimizer saying this or that, why the hell is this unconstrained. If it is unconstrained means that there is some trade off. At this limit something would be happening, at the other limit something else would be happening. Somewhere in between is the optimum, right? Trying to understand this will make you a better and better engineer. If you don't try to understand this, you can do n number of optimizations, you will remain a fool. Came in a fool, went out a fool. A fool can still claim that, oh, I didn't have the benefit of an optimizer. You can't even claim that. Do you see what I am saying? So, what the hell was I saying? Choose MVs for active constraint control that are as close as possible to the constraint. More fundamental than this, try and interpret why is the constraint active. Why does it make economic sense to have the reactor at max level, temperature at max, this column at its flooding limit, etc., etc. That I am assuming anybody who does the optimization would do this before recommending implement this as your plant operating policy, right? So, okay, there are active constraints, and the rule of thumb for those active constraints is, well, if the constraint is active, you want tight control of that constraint, and therefore for tight control you need a manipulated variable that is close by, so the dynamics of that loop is fast, so that it can be tuned to be really tight, so that the variability in the constraint variable is small. If the variability is small, you can operate closer to the constraint limit. Back off would be smaller. So this minimizes back off, right? Done. So handling active constraints makes things very simple. These are active constraints, these need to be controlled tight. What is the nearest MV that is available for controlling this active constraint? Well, that's what needs to be implemented. Yeah, okay. Unconstrained degrees of freedom. I spent a lot of time trying to explain to you that, look, in order to have a simple control system, the dirtiest approach is, well, for every disturbance I will re-optimize. So today my production rate is 100 kilomoles an hour. Let us say my unconstrained degree of freedom is reactor temperature, for the sake of it. Today my production rate is 100 kilomoles an hour. Optimal reactor temperature from a model by an optimizer run blindly comes out to be X. Tomorrow my production rate is 130. It comes out to be X plus, I don't know, X plus maybe A. Okay, I can keep doing my optimization again and again and calculating the optimal value of the reactor, my unconstrained degree of freedom. That's one way of doing it. Problem is, it is not simple. It depends on the fidelity of your model, etc., etc. You may, for example, find that instead of controlling the reactor inlet temperature or reactor temperature, you are better off, for example, controlling the inlet temperature minus outlet temperature. That comes out to be nearly constant, whether the throughput is this or that or that. Does that make sense or no? So now you are saying, instead of controlling reactor T, maybe you should control reactor delta T, because it is what? Self-optimizing. Because holding this constant is economically sound, right? So this is the idea of self-optimizing CVs. Much thought needs to go into how I select my unconstrained, what CV is selected for handling unconstrained degrees of freedom. And this is what distinguishes good engineers from bad ones. This is what distinguishes the wise guys from the fools. Okay? A good engineer will be able to tell you, well, instead of controlling this, why don't you control this? This will work not only at this disturbance value, this will be reasonable even at this disturbance value. It is insensitive to the disturbance, right? That's the whole idea of, that's what distinguishes a good operator from a bad one, a good control system from a bad one, a good engineer from a bad one.